Right, so again, Matsubara range function G tau. As I said, it's quite important, especially in the DMFT field, to be able to understand from the G tau on the G of I omega n how to extract all the physical quantities which I mentioned. And so what I would like to discuss a little bit is how does a green function look like? And you know, I plotted before self-energies and green functions, and especially if some people who are trained with more formal trainings on green functions, which are these mysterious objects with branch cuts and everything there, the fact we can actually plot them into a computer is maybe not so common. So I like to see, where do I find the information in the Matsubara green functions? So I'm going to make pictures. So I'm going to take a G of tau, and I'm going to take a local function here, local green functions, because mainly it will be impurities later, so I will forget any K space at this stage. And I'm going to make a picture. So that's a sketch. We'll see many of them, of course, during the exercise. So as a function of 0 on beta, the function will look something like that. So it will have the following properties. So first, G tau that's a formula I already wrote before, A of epsilon, exponential minus epsilon tau of 1 plus exponential minus beta epsilon. So in particular, G tau is always negative. It's always negative. In tau, we're talking about the diagonal green functions. If we have off-diagonal, it's different, but let's do one thing after another. Its second derivative with respect to tau is also negative, meaning the function is concave. Because if I do a second derivative here, I will drop an epsilon square. A is positive. So this is positive, therefore everything is negative. So we have these two properties. And we know the value on these 2 points. We know that the value at tau equal 0 minus is going to be C dagger C, meaning the number of particles. No. The number of particles, and we know that the function at tau equal 0 plus minus at tau equal 0 minus, you can look at the definition of the function that will give you, so from the definition minus the anticommutator of C and C dagger, will give you -1, that's a discontinuity. So if I were to plot the function on the whole axis, it will look like this, with beta antiperiodicity, but it's sufficient to know the function here on 0 to beta. We have all the functions. The special values that we have here, because the function is beta antiperiodic, here the value is average of n. I forgot an average here. Average of the number of particles. Minus. And here it's -1 plus average of n, because the sum of the two, g of 0 plus, minus this, which is plus g of beta, because the function is antiperiodic, is give me indeed -1. So the function will look something like that. It's concave. They all look the same in this way. Okay. A very interesting and special case which you need to be able to recognize, is the particle hole symmetric case. And in this case, the function will look, okay, that's a difficult thing to do, of course. The point is, it will be, it's hard to draw on the board, but it will be symmetric with respect to this. It will look symmetric like this, from minus 1/2, minus 1/2. The particle hole symmetric transformation in this language is g tau gives g of beta minus tau, as you can check as a little exercise. Check that this transformation is equivalent to changing A of epsilon into A of minus epsilon, which is a particle hole symmetric transformation, by using this relation. So in the case where it's particle hole symmetric, G beta minus tau is G beta, so it's symmetric around beta equal over 2. So it's an important case to check, in particular when you do calculations, because it's usually the first that will work properly. And so it's an important one to be able to recognize. And of course, the particle hole symmetric in the spectral function means that it's symmetric positive and negative frequencies. Okay. Now, let's look at such green function in an insulator. Well, first, even before, where is the long time? So in such a function, we have this is the short time around tau equals 0. This is also short time, negative times. The long times are here, close to beta over 2, and that's, thing. So I'm going to elaborate a little bit on that in the question in the metal. But if we want to see the low energy behavior, meaning the long time behavior, we are going to look in the region close to beta equal over 2. So let's first look at two cases, a metal and an insulator. So let's look at in an insulator. Again, I'm going to use my baby problem about atom. My spectral function, which I have derived before, in the particle hole symmetric case, and therefore the green function is 1/2 exponential minus u over 2 tau over 1 plus some uninteresting quantities, plus exponential plus u tau over 2 divided by 1 plus exponential beta u over 2. What matters is this thing here. So especially this one. What we are going to see in an insulator is that our green function, as a function of tau, will drop here exponentially. Let's concentrate on the first part at tau equals 0. you will drop like exponential minus the gap energy times tau here. And of course, the same here. And here you'll be very close to 0 because you'll be exponentially small. So if you have an insulator, you will see the gap in the functions. And how do we know that? In general, because it's always the same formula. There is one formula you need to know, which is this one. So if A of omega, A of epsilon is something like that, let's say with a symmetric gap, just to make life simpler, E gap, E minus gap, minus E gap. Clearly, the integral will only start here at E gap, and therefore the exponential will be dominated by the first non-zero value of A, which means going to be exponential of the gap. So if you have an insulator, you can find the gap. There is no need of analytical continuation to have omega. You can find it by looking at the exponential decay of your function here. You plot it in semilog, for example, and you'll be able to find it. So that's the insulator. Now, the metal is a bit richer, as usual. There is the metal. In a metal, at 0 temperature, and the Green function, we know, for example, a spin-spin correlation function decays. How does a spin-spin correlation decays in a metal? Anyone? Just check. 1 over time square. Here will be 1 over time for the retarded function. So we like to see these things in the Fermi liquid. Huh? So how do we see that? That's harder because we are talking about long time limits here. So we like to see that we have here beta over 2, beta. So we have a short time regime here, which is not that. It's a bit bizarre, short time regime. Short time regime, which is not very interesting. But here there is a long tail, which is going to go like 1 over tau. And then, of course, the function will just do something more or less symmetric here. And here, in this region here, in these asymptotic regions, you're going to find the long times. So to be more precise, the long time limit will be when the temperature goes to 0, meaning that beta goes to infinity, the time goes to infinity, but the ratio tau over beta is fixed. In order to reach very, very low energies, of course, you need to go to lower and lower temperature. You're going to stretch your function. It's going to be longer and longer. And the regimes, asymptotic regimes, are around tau over beta large, but close to beta over 2 is going to be the long time behavior. And then the second part of the function here is a negative frequency, right? The other part. So here you want, in the metal, the signature is that you won't have an exponential decay, but a power law decay. Yes?
Asymmetric or not asymmetric?
Doesn't matter. No, it's not necessarily symmetric. Now, we can, so you will find the power law here that indicating that you have spectral weight at 0 frequencies. Because if you have a gap, you will see an exponential. If you find power law, it means that you find the spectral function, which has some value there. Good. So one can be a little bit more precise and saying that in this regime here, in fact, the Green function g of tau is proportional to the spectral function at omega equals 0. If it's not 0, times pi over beta divided by sine, pi tau over beta. If you look at this function, indeed, in the long time regime, I mean, close to beta over 2, it will behave like 1 over tau, and it will just find the scaling, the shape of the scaling of the functions when you are in this regime. That's one way also to recognize the method. You can plot your green function g tau as a function of this sine, or the log of the green function as a function of the log of the sine. It's one way to be able to analyze it. The other thing is that you can find that g at beta over 2 is probably close to a of 0, so a good indication that you have spectral weight at 0 frequency is the fact that the function at g beta over 2 is an indicator for it at low temperature. That's only valid when beta goes to infinity. So if you're at finite temperature, you should be a bit careful about that. But so this expression here, I don't want to do all the derivation on the board because it's a bit cumbersome, but I can give it to you. It's nothing more than the famous expression we had before, the Laplace transform, where you take the long tau limit into it, and you will see the function only at 0 frequency. So I can give you an idea how we derive this. You take this, and then you change to a variable where you scale out beta in these equations. The scaling out will just spin the function at omega equals 0, at epsilon equals 0, and then you have an integral here, which you can, which is a special integral that you can very quickly find, or that Mathematica can do, and get this typical form, pi over beta over sine pi tau over beta. So it's, you know, that's how things will look in a Fermi liquid. We can look at things also in frequency. By the way, if any of you has done a bit of conformal field theory, it's less popular these days. This is a completely classical form when you go from 0 temperature to finite temperature to a cylinder due to finite temperatures transformations. So that's the asymptotic form. So in some of our papers, we actually plot the log of this versus the log of this to see it. Now, what about frequencies? How does it look like? All right, so I'm going to plot two functions in frequencies. It's supposed to be at 0. Huh? Of course, we're talking about Matsubara frequencies. So they are discrete in the frequency axis. I'm just drawing a black line as a guide to the eye just to see the functions. The lower the temperature, the closer your Matsubara frequencies are going to be, because we know that omega n is 2n plus 1 pi over beta. So the larger beta, the smaller the interval becomes. And if you have reached the low temperature regime, you will see, if you compute lower and lower temperature, your curve will, the red point will slide on the black curve, which is a final 0 temperature regime. So I'm just drawing that, and then I'm asking you a question, which is the following. This is a green function g tau This is also a Green function g tau in frequencies as a function of omega n. Which one is the metal? Which one is the insulator? Yeah, so one at a time. Who said something?
I think metal on the left and on the right is insulator.
So you say that this is the metal, this is the insulator. Anybody disagree? Okay. Well, unfortunately not, is the opposite. And the reason I'm doing that is indeed that it is very, it is deceiving. We should be, so I'm going to explain why. This is, let me get it right, if possible. Yes, this is, what did you say?
Maybe because there is a pole, it's right.
Okay, anyway, this one is the insulator. This one is the metal. Maybe you said it correctly and I misunderstood. But
No, I said wrong.
so the reason is that it's very deceiving because you think that this looks like a divergence and everything. Of course, it's a finite number here. There is a finite jump here. And how do we know that? First, let's look at the insulator case. Again, we are going to use our magic formula, the spectral representation. If we look, so this tells me one thing. It tells me I can continue my function in the entire complex plane, z minus epsilon. And in the complex plane, in Z, this is the real axis, omega, that's a Z plane, and I will have my Matsubara frequencies on the imaginary axis, right? That's the analytical continuation form. If I put I omega in here, I have my Matsubara functions. If I have, that's this. If I put z equal omega plus I0 plus, I will get the real function. And of course, the function has a cut here along the real axis. And is analytics in both upper and lower half planes. That's the structure of these functions. So if I go, the key question is what happens when omega goes to 0? When your omega goes to 0 here, if you are in an insulator, it means there is maybe some spectral function here, but there is none here, meaning there is no branch, there is no cut in the function here. The function when omega goes to 0 here is going to be, no, I don't want to paste anything. The function when omega goes to 0 here is going to be continuous. So, in general, if you take the difference between coming from above and coming from below, positive and negative imaginary frequencies, you will get something like d epsilon a epsilon 1 over omega minus I0 plus minus omega plus I0 plus, right? And that is more or less delta of epsilon. So you will get something like A of 0. So the discontinuity that you will find here when you go from negative frequencies to positive to negative frequencies by crossing the real axis is going to give me the density of state, the spectral function at 0 frequency. So in an insulator, it's 0, and in a metal, it's a density of state. So the point here is, and it gives me an estimate of the density of state, of the spectral function, sorry. The point is, in order to recognize the different objects, metal, insulator, from Matsubara, you need to do this little exercise. You need to take a little example with an A of epsilon, compute it, and actually plot it, maybe on the computer, in both cases, and learn how to recognize these different parts, because it's not necessarily intuitive. That's the reason for this exercise. And finally, if I look now at the self-energy, well, the self-energy has a very similar behavior as in the real self-energies. And I'm going to plot what the self-energy would be for a metal. We would have something like that. And again, some Matsubara frequencies. The only real, what did I do? Yes, that's the imaginary part of the real of the self-energy. The only difference with before, which you should pay attention to, is that the self-energy is giving me, of course, the self-energy when the real part, when omega n goes to 0, plus 1 minus 1 over z times I omega n plus the rest. Now, because the frequency is imaginary, the quasi-particle residue is in the imaginary part of the self-energy, not the real part. So we'll have here in the imaginary part of the self-energy, the rest looks very similar. Little remark, in a Fermi liquid, because if we look at the first, well, I omega n, we have some constant plus some 1 over z no, okay. This thing doesn't really work. You have something which is an imaginary constant, a constant here, times omega n square plus pi t square, plus order terms, just higher order terms. Then the self-energy as a function of the first Matsubara frequencies, which is I pi t, we'll get something constant, a term here which is proportional to I omega naught, which is therefore proportional to t. And the first term here, because omega naught is pi t, is going to disappear. So there is no t square term plus t cube. So if you plot as a function of temperature the self-energy at the first Matsubara frequency, you will see a very nice linear regime plus higher order correction. The t square disappears. It's an excellent signature of the Fermi liquid because it tests the fact that the imaginary part is indeed properly omega square plus this. This usually called from paper by Maslov and Chubukov. We call it the Maslov-Chubukov trick often. So it's an excellent signature of Fermi liquid in self-energies. Yes?
Was the image of the self-energy this
Louder, please?
Was that cartoon of the self-energy versus Matsubara pieces from metals or insulators?
That's Fermi liquid.
Right, but then when we did for the Hubbard atom, we had the self-energy going as 1 volt omega. So we had this tail. Would it the same behavior here?
No, yeah. That's for Fermi liquid. I was going to finish with a remark exactly on that, on insulators. So just wait for a second. Yes?
The graphs we plotted before
Yeah, for the green function. This is the self-energy.
It was the green function of I omega n, right?
Correct.
We want the g of tau.
Correct. Oh, I'm sorry. You should have told me. My mistake. Of course. Is g of I omega n. Yes, thank you. And I wanted to finish on precisely your question about the self-energy in insulator. As we say in the Hubbard atom, we get self-energy equal to U square over 4 I omega n in the particle symmetry case, so it may diverge. But if you shift the chemical potential, you will find something that will look like something like that as well, because it will look like constant plus constant over omega minus constant. So you don't know anything. So the methodology here, and that's important, first you look at green function, identify where you are, and then in metals you analyze the self-energy. Don't skip the steps, because it's very easy to find the self-energy that looks whatever you want in a bond insulator or somewhere, and then go into wrong conclusions. So I guess it answers this question. Very good. Good. So I have two things. I have one thing about the representation of green functions or quantum impurity models. So either we switch now or later. Oh. No. No. I have a couple of slides to finish on the green functions, if it's not too difficult to switch. And then I will do impurity models, and at least start impurity models. Right, okay, so now I've shown you some sketches, how the green functions are, how they look like. Now I would like to answer one question, and that's more recent material, it's not really standard. How do you represent G tau into a computer? We are going to do numerical methods. We're going to represent that. So it's an important question to deal with. And remarkably, there's been in the last years important progress in this. So I'd like to take a few minutes about these. The slides will be also available separately. How do you store G tau? Well, the simplest way to do it is to take, in tau space, and you take a linear grid in tau. Okay? Very simple equispace grid in tau. That will require a number of points that will scale like beta. It's relatively a low order accuracy because your function, as you can see, your function will bend at boundaries. If the temperature becomes very low, the function can very stretch. It's very flat and very sharp, close to tau space. But it's basic representations. In omega n space, you can say, I'm going to take a finite set of Matsubara frequencies with n less than some cutoff. The problem you have with that is that you need to deal with the convergence with this cutoff. The function has tails. I didn't say it again, but because the green function has, you can see that from the spectral representation, you take the long omega limit, the function becomes like 1 over omega at large omega, 1 being the discontinuity in tau space. Because the function is discontinuous in tau space, its Fourier transform has to go slowly as a function of frequency. So we have to take care of all of this everywhere, in sums, in Fourier transforms. So it's not ideal. There's a second idea which we put forward a few years ago, which is to use something very simple, after all, orthogonal polynomials. Your function is a very smooth function between 0 and beta, so you can see it here. I don't know if you can see the mouse. Can we? Yes. So that's again the same sketch as my notes. So on this part 0 beta, you have a very smooth function. You can extend it into Legendre or Chebyshev polynomials in this way by saying g tau is the sum over gn Tn of t beta, t over beta. It's quite efficient. The coefficients will decay exponentially after a while. It requires less coefficient. You can enforce discontinuity on tails, and it can be, in some good case, well, if you do it well, it's quite quick to evaluate as well. You can also do it by panels. These are refinements which are well known into orthogonal polynomials techniques. But there are better techniques which have appeared since 2016, and an important work by our colleague Hiroshi Shinaoka in Japan. The fact is, as I said, G of tau does not contain all the information of the spectral function. This is again the spectral representation A of omega k tau of omega, the same function I wrote many times. I just isolate k as a function of tau and omega as a matrix. And again, the problem we have with analytic continuation is that you can view this as a matrix multiplication. The problem you have is that k is of low rank, very low rank, because of the exponential omega tau. So it's a big problem for analytical continuation, and people for years have said, that's a problem. And what Hiroshi said is that, well, no, in fact, we're going to use that to our advantage because it's low rank, its image, the space that it spans, is of low dimension. Therefore, we should be able to parameterize G of tau with a few numbers. So the way I'm going to present is not the original one, it's a slightly different one we developed at CCQ, but that's the one we are going to use in the tutorials. If we view that as a matrix, K, and I'm going to put a grid in omega and tau, there are ways completely controlled mathematically to do that, and I'm not going to bother by that. The point is K is spanned by only a few columns. So as a result, you'll be able to write G tau as a sum of a finite number of exponentials, and I can give you the exponentials. I can give you the omega L's, and of course then you need to fit or determine the point GL. And if you give me a position and you give me a temperature, I can guarantee that I can write this function as a sum of a finite number of exponentials. Why? Because my matrix has low rank, I can select a few columns and reconstruct all of the other from the columns I've selected. That's standard decomposition, interpolating decomposition. Typically, it's a QR decomposition of the matrix. So you select, so that's linear algebra. You select a couple of frequencies. Well, the linear algebra algorithm does for you. And therefore, the matrix K of omega is just a linear combination for every tau of K of tau of omega L times some coefficients, which we don't know at this stage. If that's true, then I can report in my equation here and find that G tau is indeed K times some function rho, and I expand that, compute the coefficient, and indeed I find it is a sum of a finite number of frequencies. Now, the point is, these frequencies are few and universal, quote unquote, in the following sense. If you give me beta and a high energy cutoff, and the precision at which you want to represent your function, and I don't know why the slide has not changed. Okay, it's a bit erratic because it doesn't change with my computer. So. Okay, now it's fine. Then the number of exponential I need is logarithmic in temperature and logarithmic in precision. So temperature over high energy cutoff, the highest energy scales to the lowest energy scales, which is quite small, meaning you can get away with 20, 30 typically. And it's universal, meaning that I can guarantee that every Green functions respecting that high energy cutoff and the spectral functions and at temperatures is going to be represented by these exponential. And we can pre-compute them a priori, because they're just function of the K kernel. It doesn't depend on any green function. So that's what we can do. These are, for example, some of these frequencies that we can determine for some cutoff. And when you have that, then you can do several things. You can fit your functions, for example, because you know its form. And its form is extremely simple. In fact, there are 3 ways to represent it. The function is determined by its coefficients, as I wrote before, but also on 2 other things. There are endpoints and very special points in tau I, which we can determine with similar techniques called collocation point, where if you know the function at that point, then I can reconstruct the coefficients and the sum of exponentials. It's like the collocation point for orthogonal polynomials. And these are the tau points, which are determined in some cases. As you can see, they accumulate to the boundaries because the function is very sharp to the boundaries, so it has to be able to represent that. The second way of using the same technology is that we can, in fact, find a subset of the Matsubara frequency, again, a universal subset where I can represent the function. You only need to know it on n Matsubara frequencies, and that's it. You don't need to know the rest. You can deduce all the rest. On a trivial example of application, you will have to do sums, this kind, which of course in realistic cases, as you will see, are far more complex than this simple example. But then you can do it only on a subset of omega n, which is much smaller, which is only logarithmic with temperature. And as you can see, this is a relatively recent discovery, a couple of years ago. Now, the original version by Shinaoka is called the intermediate representation. The one we have here, I forgot to name it, is called the discrete Lehmann representation. Why? Because it's like the Lehmann representation, except it's a discrete sum rather than a full integral. And the 2 representations are very, very related. DLR is just decomposing the K matrix with a QR. The other one is an SVD, it's slightly different. The point is you have 2 bases. The IR is an orthogonal basis, but it's not as explicit. It's not a simple exponential. You have to represent it. DLR is explicit, but not orthogonal. And again, the slide has not appeared for a mysterious reason. Yes, it's painful. Now it's synchronized. So again, DLR is a very explicit basis, pure exponentials, but it's not orthogonal. IR is an orthogonal basis, but not explicit. So what is the best representation? Well, it will depend on usage. As usual, since the dawn of computer science, there is a trade-off between memory and speed. If you want to compute quickly, if you want to store in memory, there are slightly different constraints. In practice, what we use in the tutorial is a linear grid. There's still many tutorials, and it's simple, and the DLR. So there will be an exercise to see that. It's just to show that representing these functions can be done in a very parsimonious way, in a very compressed way. That's point number 1. Point number 2, I mean, this has been introduced in the 50s, and you have seen this optimal representation have been discovered 10 years ago, which means that even on the very simple objects like G tau, still things to do. Maybe not G tau, but slightly more complex objects. And we have implementations. I don't know why we have code. There's no need of a code here. Yeah. Of course, in Trix, you will see that. The library is a piece which is a bit separated. You also use separately. It's called CPPDLR. That's been done at the Flatiron Institute. All right. That's what I wanted to say about the representation of G tau, not just on sketches, but on the computer. And you will play a little bit with that. Questions on that? Yes?
Does the misconvergence of the Matsubara frequency depend on the spectral function? Because you said that this doesn't depend on the system.
It's an excellent question. So, I mean, either form, this form or the form in frequency, are universal in the sense it only depends on 3 things. The precision you want to have, the maximum cutoff that you put on the spectral function. There is a physical cutoff that you need to, because you need to have a maximum energy scale. Otherwise, you can have a function that can do everything, right? And the temperature. So it does not depend on the very precise spectral function for a given function. in that sense, it is universal. I can get a set of omegas, and I will represent every function. It's not necessarily optimal. For a given function, you may find a better set of exponential even smaller for a given spectral function, but that's a different question. So here, yes, it's universal. And I put quotes because it's universal in the sense I said, but there are different choices of omega n to decompose my matrix because it's of low rank, so I can choose different omegas, and the algorithm can choose different omegas. But once the set of omegas is fixed, it represents everybody. Okay?
It depends on the system. I mean, fixed A of omega, you have to, the integral depends on A and K. So the integral depends on the system that you're dealing with.
It only depends through omegas and omega max and beta, not of the details. So if you know it a priori, you know that you have the exact form, you can fit your function into it. So it depends on a very, very minimal notion. And even, now I didn't insist on that, but even in a metal, right? In a metal, I can represent as a sum of exponential, which may seem contradictory to what I said before, because in an insulator it's exponential, in a metal it's 1 over tau, but on a finite segment, I can represent the 1 over tau function for a finite length with a finite number of exponential. That's what the mathematics do for you. Anyway, that's just to introduce a little bit some numerical techniques, and now I'd like to go back and spend the last part to start quantum impurity models, unless there are other questions. Michel, can you? Yeah, thank you. So now we are equipped with, and I'm more or less on time. Maybe I need a few more minutes, but that's fine. Now I'm going to, we have the basic tools. We know how to read self-energy, at least the basics, and grain functions. Now we're going to start to study the building block of DMFT, which is impurity model. And of course, I'm going to start with a non-interacting impurity model. I will use some of the tools I presented before. Now we are going to go into, almost DMFT. Okay. Non-interacting first. So my Hamiltonian will be the following. I'm going to look at H with one level, D, coupled to a bars of non-interacting fermions, no interaction, no spin. So U equals 0, no spin. And I'm looking at epsilon D, D dagger D, plus sum over lambda, 1 to N lambda, of epsilon lambda, C lambda dagger, C lambda, plus some hopping between the two. V lambda, D dagger, C lambda, plus V star lambda, C lambda dagger D. So this is a level, D, coupled to a bars, that's the C's, different levels. It could be continuous, whatever. And I can hop from the site to the bars and back. It contains two things. I can have D as, real translation invariant bars, like a Fermi C. In which case lambda is equal to K. Or it could be, well, I don't need to redraw it, something like that with a couple of states which are whatever they are, like they will be in DMFT problems. They don't have any special meaning. They're just defined like that. Right, so that's a simple problem. It's quadratic. So because it's quadratic, we can solve it. We're going to solve it. So what I want to compute is the green function of the D and the spectral function of the D. So to do that, I'm going to define psi, meaning C lambdas, D, kind of vector, with all the C's and a D. My Hamiltonian is now therefore rewritten as C dagger M psi, where M is a matrix which is epsilon lambda 0, 0, epsilon D, V lambda star, V lambda. Okay? I've done nothing, just rewrote it as a matrix form. You stop me if something is not clear, right? Well, I gave you the result before. The green function of I omega n is the inverse of it is therefore going to be I omega n minus m, meaning I omega n minus epsilon lambda minus V lambda minus V lambda star I omega n minus epsilon d. So, and this matrix, of course, diagonal, this is 0 here. So the only thing I need to do to compute my green function on the D is to compute the inverse of this matrix and look at what is in the corner. My green function G will be a big matrix CC, CD, DD, DC. And what I'm interested in is to compute this. What is the green function of the D in the presence of the bars? Well, I'm going to pause for a second. The problem is, I want to inverse the matrix like this. I'm going to give you the mathematics. Just to do that, give you the formula, then applying this formula, we'll get the results, right? So, well, I can write the results immediately. Oh, no. GDD over omega n is going to be I omega n minus epsilon d minus sum over lambda of V lambda 1 over I omega n minus epsilon lambda V lambda star. No, what is this? Inverse. What's happening? What is it doing here? Just that, yes. So now, how do I do this calculation? The problem is to inverse a matrix like this. There are different ways to do it. I'm going to give you the formula on how to prove it in a completely general way, and then you can use that to compute this. So the problem is a little mathematical interruption. That's linear algebra. You have a matrix A11, A12, A21, A22, and you want to compute the inverse of A in the block 2, 2. Okay, fortunately for us, this is well known. That's called the Schur complement. So, okay, doesn't want to do anything, but is denoted this way, and is defined by A22 minus A21 A11 minus 1 times A12. That's its definition. I just define this way. And then the result is that a minus 1, 2, 2 is equal to, where is it? Yes, well, the inverse of the short complement. That's the formula. You define this, just a definition, and the inverse of this is what you're looking for. Now, I let you do the exercise of taking the matrix I wrote before, apply the formula, and see that indeed I find the formula I wrote. It's just one-liner, you do that. Now, this looks maybe a bit mysterious. Who is familiar with the short complement? Ah, a couple of people, good. But not many, so I will tell you. There is another formula, by the way, which we don't use, which you may be a bit more familiar with, is that the determinant is going to be the determinant of A11 times the determinant of this short complement. I'm giving you the formula to check how exactly to check that. It takes 2 lines, so I'm just giving it to you in the following way. You're saying that A, which is A11, A21, A12, A22, and that's the whole trick, is 1, A21, A11 minus 1, 1, 0. I forgot to say that I'm supposing that A11 is invertible, which is the case in our calculations, A11 being the C's, yeah? Times A11, A over A11. Okay, when we need it to move, it doesn't move. One, 2, 1, 0. Just this formula, which you can check by direct inspection. Just do the product. And you will see, that's by, of course, the matrix is by blocks. You do the matrix products, and you will check that this is indeed correct. And then you can compute easily the inverse, because the inverse of a product, that's, of course, the inverse of this times the inverse of this times the inverse of this. And inverting a matrix like this is trivial. It's a transvection. So you will find that you have the inverse of this times the inverse of this times the inverse of this. I don't know if I need to rewrite it. And well, you have A minus 1. And then you compute the two components for this explicitly, and you have finished the proof. So inverting this matrix is a well-known problem, which I gave back the formula here. So that gives me the solution of my problems. Really, the only thing is this trick here. There are many ways to solve this problem. I just, since it's a solvable problem in mathematics, why not use the formula? Okay, so can I return, yes, to the formula here? So applying this formula, I will find this, and therefore, I want to write it, and that I will write into more functions, that it's an important function to introduce. The results which we have, GDD over I omega n minus 1 is I omega n minus epsilon d minus delta over I omega n. And delta is what I wrote before. I'm just rewriting what we had before. V lambda to the square divided by omega n minus epsilon lambda. This function here is called the hybridization function. It plays a major role in impurity problems and DMFT. It represents the effect on the bath, of the bath onto the impurity levels. So you have a level epsilon d coupled to the bath. All the action of the bath is encoded in delta. Now, you can ask yourself a little bit, what these things means. Is there any question at this stage on this? This is an important function. We're going to see it again and again. Yes? Yes, it's a very good question. It looks like a self-energy, right? Yes. It's not a self-energy because it's not the effect of interactions. It's just an interacting problem. But it's a matter of point of view. If you look at an expansion and you do the V term, which connects the two as your perturbating vertex, then it's a self-energy in that expansion. But it will play a role similar to the self-energy. It will go close to the self-energies. Technically, it's not a self-energy. Sure.
If that would be just Green's function, not Green's function dd, so part of the Green's function, then delta would be self-energy. But because we consider only...
It's a matter of semantics. It's just we usually use self-energy when there are interactions. This is a non-interacting problem. But, it's a matter of naming, nothing more. You're correct that if you look at the full Green functions, okay, I want to go back to it. No. What happened? I just wanted to go back. Oh no. Ben ouais, voilà, c'est juste... Okay, let me finish the lecture and try to recover from that. Oh, great. Wonderful. Yeah, thank you, but I was supposed to use what I had before, so it's not great, but okay. Wonderful. Okay. What was I doing? I was answering one. I wanted to go back, but I can't. So the fact is that if you look with the matrix form, then your self-energy, quote unquote, would just be V lambda. It's just a number. Okay. What we are doing here is we are integrating the bath. That's what I would like to do just afterwards. So there are two ways to do that. You look at the big space, and then you have a big matrix, or you look at only this space, and you're integrating the other ones, and then you have a function which depends on frequencies. So that's what I wanted to do. We may look for, maybe we should look afterwards, and it's okay, I can just wonder, but I just didn't do anything. Anyway. Yes, so, well, you have noted everything, I guess. So I'm rewriting delta omega n. Of I omega n minus epsilon lambda. So first question is, what is the interpretation of the hybridization function? You can interpret it in the following way. I can write GDD of I omega n as 1 over omega minus epsilon d times 1 plus v lambda. So I can expand the equation for GDD was v lambda times 1 over I omega n minus epsilon lambda v lambda plus higher order terms. So if I denote GD0 equal to 1 over omega minus epsilon d, and G lambda 0, 1 over omega n minus epsilon lambda, then I will have an expansion of this way, which is GD0 over I omega n plus GD0 over I omega n times V lambda, G lambda not V lambda, GD plus higher order terms. So if you write in a pictorial way, meaning in diagrammatic expansion, the DD functions will look like the bare D function, GD, plus the bare green function times a V times here G lambda functions times V lambda star times GD, plus the next ones, like this, etc. In other words, it describes the fact that the electron is coming from the impurity problem onto the bars, spend some time into the bars, then come back into the impurity problem. And you can do it once, twice, 3 times, 4 times, as many times as you want. So this delta function describes the excursion of the electrons into the bars. And because it's a quantum problem, of course, this depends on time, therefore on frequencies, because it describes the retardation effect that you have when you do all of this. Okay. So that's what delta is. Now, a especially interesting case will be, a priori, in a continuous system, you have a continuous limit, so delta will be a continuous function. In an infinite system. So imagine we have a Fermi C. Then delta of R will be the sum over K of Vk squared of omega minus epsilon K psi 0 plus. And this function has a spectral function which is imaginary part of delta of omega equals sum over K over Vk squared times delta of omega minus epsilon K, which is whatever it is. And in simple cases, especially if you consider simple impurities in real metals, your function may be whatever it is. And we can take an approximation that the function is basically a square, a constant, plus a very large energy cutoff, d minus d. So we can concentrate at low energy onto a function that will be almost like a square. And if you do these calculations, you'll find out that delta of omega close to 0, retarded, is going to be a real part, a number, which will shift the position of the levels, minus I pi v square times rho naught, which is the density of states of those electrons here at Fermi level. So if I call gamma pi v square rho naught, then my green function will become GD R of omega, 1 over omega minus some renormalized levels, which contain the real part of delta, minus I gamma. In other words, if your hybridization is just some Fermi Cs, the only thing that matters is the density of state at the Fermi Cs times the hopping at the Fermi level. And this tells me that the spectral function of the D is basically a Lorentzian of width gamma, where gamma is given by this, at the position epsilon d tilde, which is epsilon d plus real part of delta r. Okay, so you have a level, you connect it to a Fermi C, and you end up with a resonance, which has a width and a lifetime gamma, which is given by that. This has a name and is well known. Fermi golden rule. You have a discrete level coupled to a continuum of states. Your level will decay with a lifetime, which is given by the hopping times the density of states at the Fermi level times pi. Okay? So we recover that in that very simple case where we can approximate delta simply by a lifetime.
Question?
Yes?
Sometimes you write delta retarded and sometimes not.
Because I forget. It's all in real space here. Sorry. It's all in real frequency, so it's all retarded. Okay. Fine. So how am I doing with time? 4 pages. All right, of course I need to rewrite something because... All right. So what I like to do next is do a little bit, and elaborate a little bit on the answer I gave previously, and we mean by integrating the electrons. And to do that, on this part only, I will use a little bit of path integrals, but just a little bit. If you're very familiar with it, no problem. If you're not, you don't need much. Maybe you want to learn more about Grassmannian path integrals later. But it just introduced a form that will be the form in which we write the DMFT equations. So I'm going to rewrite this into an action form. All right. Okay, so I have to rewrite H. Okay, that's the Hamiltonian we had before. Okay. And what I want to do is that I want to compute the partition function, and the partition function is equal to the integral over the D and over the C, or minus 1 of the action as a function of C and D, where S is the action. The action as a function of time has its standard form, which is